about work. We have discussed about internal energy. We have discussed about heat. Now we are going to discuss about work. Okay. So work, we generally, whenever we say work, we always understand mechanical work. That is, some displacement has taken place along the line of application of force. Okay, but actually, there are three types of work side. Normal work, whatever we say, that is nothing but the mechanical work. Another two types of work are electrical work and the gravitational work. Okay, so when if the definition of work comes, you just give the definition of a mechanical work. Okay. Work is said to be performed if the point of application of force is displaced in the direction of the force. It is equal to the product of force and displacement. The work is always composed of two factors. And intensity factor. What is intensity factor? It is a measure of force against which work is done. Second, a capacity factor. It is a measure for the extent for which the work is done.
So done.
Okay. On the basis of modes of energy transferred, work can be classified into three categories. One, mechanical work. Second, electrical work. Third, gravitational work. Okay, now what is mechanical work? Mechanical work, I told you, force into displacement. So, mechanical work. Okay. Equal to what? Force into. Okay, now let me come to the intensity factor and displacement factor. Okay. So now we know that W is equal to F into distance by which it has traveled. So here, intensity factor is F, you should know. And capacity factor means displacement. It is the extent up to which the work is done. And it is a force which is responsible for the work to be done. Okay? Now, when you go for electrical work, what happens in one place? Suppose electron got deposited. Then after that, from there, the electron starts moving. All right? Huh? Electrical work. So here, intensity factor into capacity factor. So here intensity factor is what? EMF. Charge is building up. And quantity of electricity. See, when electron starts flowing, then only we say it is electricity. So what is this EMF? Is E0 cell. And it is N into F. So because of that, what we write? Finally, we write here N F E0 cell, but we put a negative sign because it is the question of negative charges moving. Okay. So now, third is gravitational work. See, gravitation on the basis of gravitational force only. If you leave an object, it directly goes down. So in gravitational work, what is the intensity factor? Your intensity factor is mass into gravitational force, and displacement is h. So therefore, W is equal to mg.
Sir, done.
Okay. Now you go for sign convention of mechanical work. Sign convention of mechanical work. See here. Here, work can be done by the system or work can be done on the system. In thermodynamics. If work is done by the system, then sign convention is negative. And if work is done on the system and convention is positive. Work in a thermodynamic process. See, no solid object or liquid substance can be compressed. So, in thermodynamics, we do not consider they do any work. But the gaseous substance can be compressed or they can undergo expansion. So, work is said to be performed in thermodynamic system only by the gaseous substances. Both liquids and solids cannot be compressed. And hence, they do not perform any work. On the other hand, gases can be compressed or can undergo expansion. So, in thermodynamics, work means pressure, volume, work. Why? When you apply pressure, the volume contracts. So, pressure is the force, contraction or expansion is the displacement.
Then
Okay, now we'll try to see what do you mean by pressure volume work. So let us take a gas cylinder. Okay, and this is a this is a weightless piston. And this gas cylinder is being graduated, means you can, it is written what is the volume. Yeah, 10 ml, 15 ml, 20 ml. So graduation is there. Okay. And this is a completely airtight gas cylinder where gas is being contained here. All right. So this is the volume of the gas. The gas. Then gas undergoes expansion, and in this case you will find this is V2, volume of the gas after expansion. Okay, and this is initial. Now see here, in this case, this is the distance traveled with the gas. And A is the cross section of the weightless piston. Now, Let us consider a gas enclosed in a cylinder fitted with frictionless and weightless piston having area of cross section A. Okay, that equal to it. Let the initial volume of the gas be V1. And pressure on the piston B P internal. This is a P internal. Let the pressure outside the piston B external, where P internal is greater than P external. See, if the pressure is less here, inside is more, the piston will go up. The gas expands. And piston move upwards by a distance dl, and the final volume of the gas becomes V2. So let us see how much work is being done, because expansion is taking place. Okay. So it is P internal and of P external. So what did you find here? That P internal is greater than P external. So the expansion has taken place. So force is there, displacement is there. So in this process, some work is being done. Work done. By the movement of piston. Okay. So I'll write now here, because it did not go for a long, the expansion of the gas will not be so huge. So I've written here del W, means small amount of work. Okay. So you know, equal to what? Equal to force into displacement. Okay, now what is pressure? See here. How to relate force with pressure? We know pressure is equal to what? Force per unit area. So in this case, what is the pressure here? P internal, because it is more. So I write now here P internal equal to the force, which I did not put in symbol for force, I write force. And what is the area? Area is nothing but the area of the piston, cross section. So I write now A. Therefore, force is equal to P internal into A. Okay, now we'll go for now. So it is, I'll write again. So I'll write now here. Therefore, this is equal to what? Force is, we have got it. Displacement is what? DL. So I'll write now here. P internal into A into DL. See here. DL into A, it is nothing but the volume. This volume is the area into displacement. So how to find this volume? No problem. If I subtract V1 from V2, then I get this volume. So I'll write now here. Therefore, del W is equal to P internal into V2 minus V1. So therefore, what do you find? That this is equal to P internal into delta. So this proves the pressure done in a thermodynamic system is nothing but the product of, so the work done in thermodynamic system is nothing but the product of pressure and volume. Now, see, how could you perform this expansion? Now, you can do it by two ways. One, See, this is the same thing. Now, this expansion can be done bit by bit. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. Numerous. Just like that when, see, it is almost, does it not almost look like a hypodermic syringe? Means the syringe which is being used for injection. So whenever we are being given injection, you have seen how this pharmacist, he pushes it so slowly so that we don't feel it. So it can be done slower than that. So what do I mean by this one? That if it is a reversible process. So we can find out work done in a reversible process. Work done. Okay. Before that, I like to tell you something. See, what is that? I told you there's sign convention of work. Here, when the expansion takes place, the work is done by the gas. We do not pull the piston. Work is done by the gas. So in that case, the sign convention of the work will be plus W. And if the piston is being pushed inside, then in that case, work is done on the system. Because why? What is the system? System is gas. So in that case, if when the work is being, expansion is done by the gas, work done by the system, then we have to put on negative sign before the W. And if you push the piston inside, that is, we are working on the gas. In that case, the sign convention will put positive or will not put anything. Simply write W. Okay. Now we will mention here work done in a reversible process. So now see here. Reversible, I told you that in that case, the displacement or moment happens so slowly and such a small extent that at any moment in time, you can come back to original position. Now, maybe from moving from here to here, it may take days together. Now, how to calculate now the total work done in a system? Should you wait for such a long time? No, we will not wait, because we know that how much work is being done in each step. And if you know the number of steps, we'll try to add it. Then we can find out the total amount of work done. Okay? See here, this is the V1 and this is the V2. So that in mathematics, there is a form to find out the total thing done by several steps. Okay? That we call it integral calculus. So we are going to take the help of integral calculus. Okay? So I'll write down here. We'll write here now. The dW is equal to what? P into delta V. Okay? This much work is done in each step. So therefore, what I can do? Total work done. I write here equation 1. Done by the system can be obtained by integrating equation 1 with a limit of V1 to V2. We are moving V1 to V2. Okay? So now we write here this del W. So we write now here, this is a limit V2 P into delta V. Okay. We write now here, for an ideal gas, PV is equal to nRT, or P is equal to nRT by V. Okay. So substituting the value of P in equation 1, we get nRT then dV by V. Okay, in class 12 you learn this integral calculus. So I write now here, or W is equal to nRT, and this value gives us as ln V. ln means it's a exponential based logarithm. Okay, and this is V1 by V2, or W is equal to nRT ln V2 by V1. Now, all the calculations that we do, numerical calculations, in that case we use logarithm 10 based logarithm, or we call it natural logarithm. So if you multiply the exponential based logarithm by 2.303, you get the natural logarithm. So we write now here, or W is equal to 2.303 nRT log V2 by V1. Okay. See here now. Now I'm going to put the sign convention. This is work done on the system. And if you do work done by the system, what will happen? Then I have to put on negative sign. See here, here work is done by the system. Now expansion has taken place. So I'll write now here minus. Please remember, work done by the system. So I'll put minus. So I'll put minus. All right, then I'll put here minus. minus. I did not put it initially. Minus equal to minus. Expansion means work done by the gas. So by convention, I have to put it minus sign. We can write this equation in other forms. This is very important for numericals. See here. From Boyle's law, from Boyle's law, P1 is equal to P2 V2, or V2 by V1 is equal to, I'll put equation number. No. I'll put this is equation number 3. This is equation number 4. Is P1 by P2. So I can write substituting V2 by V1. So V2 by P1 P2. Equation 4 can be written as that W is equal to minus 2.303 nRT log P1 by P2. So this is another equation. This may come in your exam. Derive work done by a gas in a reversible process. So you have to start with drawing this gas cylinder, get up to W is equal to P into delta V. Then after that, you derive this whole thing.
Sir, done.
Okay. Now we'll go for work done in an irreversible process.
So wait. Done, sir.
See, work done in an irreversible process means what? Here we are not expanding the gas bit by bit. It has happened all of a sudden. With blinking of an eye, you have found the piston has moved from the original position to the final position. All right. So in this case, work is done in one shot. So we'll write here work done in an irreversible process. In an irreversible process, the expansion of the gas has taken place from V1 to V2 in one step. All right? Therefore, W is equal to P into, these are displacement, V2 and V1. Therefore, W is equal to P into delta V. Note for entrance. Work done in a reversible process is always more than work done in an irreversible process. So please remember, reversible process is greater than irreversible process. So now we'll go for. So these are all the preliminary information we have gathered. After this, we'll start the main body of the chapter. It is called thermodynamics. So we'll go for now. First law of thermodynamics. See, it's very interesting in your book. Even I think I also forgot to write that whenever we go for first law of thermodynamics, people has given the theory, and it is a relationship between what? Thermodynamics is the relationship where temperature is always involved. Heat is involved. So how to measure the heat? Because we know heat is a form of energy which flows from a place of higher temperature to a place of lower temperature. So initially, after the formulation of the first law, then only people have realized that we did not tell the people how to measure the temperature. So they have given a proposed theory, but that theory should have been before the first law. So what digit comes before 1? Obviously, it is called the 0. So it is somehow it is not in your book, but I'm going to teach you. So it is called 0th law. Of thermodynamics. So, okay, first I'll explain to you, then I'll write. Say you have taken a system B and A and C. So you'll find if A and B have the same temperature and B and C, they also have the same temperature. That is, we call it, they are in thermal equilibrium. That is thermal equilibrium. Thermal equilibrium. So if A and C are separately in thermal equilibrium with B, then A and C also will be in thermal equilibrium with each other. Thermal equilibrium will be thermal equilibrium with each other. So if you don't understand, I'll give you our example from our life. Okay? See, we are having fever. So we have to measure how much is the increase of the body temperature. Normal temperature, say it should be 37 degrees Celsius. Or if you go by Fahrenheit, it should be 96. See now here, when you are having fever, okay? So in this case, either the thermometer is you are being asked to put a thermometer inside your mouth, okay? Or generally at home, what we do? We put the thermometer in your armpit, okay? Armpit. This is the one. Hold it tightly. And we keep it for some time, maybe 5 minutes. Then after that, we take out the thermometer and check. So now see here what happens. Thermometer is made with glass. Okay. See here, one loop is there, glass. And what do you have here? We are having mercury. But this is mercury bulb. And what is outside? Glass. See now here. The mercury is in contact with the glass. And glass is in contact with our body. Okay? The glass absorbs heat from our body. And after some time, the body temperature and the glass temperature becomes same. So what has happened now? We find it has attained an equilibrium. The glass transfers heat to the mercury. Okay? Heat to the mercury. After some time, you will find the mercury also are in equilibrium with the glass. So what do you find ultimately? Is it not that we say the mercury and the body has the same temperature? So they are in thermal equilibrium. So from the 0th law only, the concept of thermometer was evolved. And because of that, we could find the temperature of any system at any time, and we can find which body is hotter and which body is colder. Even without thermometer also, from prehistoric days we know which is hot and which is cold. But we did not have any technique to know the magnitude of the heat content of the body. So that is called zeroth law. Actually, if this should have been done in a systematic way, this law should have been the first law. But anyway, because everybody thought that we know what is called heat, all right? And the thermometer was also being made before the law. But they have realized that we should be able to tell the people what is the concept of that equivalence in temperature of the surrounding with the thermometer. And from there, the zeroth law is started. So we are going to start the zeroth law thermodynamics first. So we'll write, if two systems are separately in thermal equilibrium, okay, we write, if you wish, you can write it here. A and C. Thermal equilibrium with a third system it is B. Then these systems are also in thermal equilibrium with each other. This is known as zeroth law of thermodynamics. So we'll write here, note. Thermometer is made on this concept. So we'll write now here, glass, mercury, body. You'll write here thermal equilibrium. You'll write here thermal equilibrium. Okay? And you write here thermal equilibrium. After writing this one, write this, then write this.
So, what's that? The thermal equilibrium with a
Thermal equilibrium. See, if two systems A and C are separately in thermal equilibrium with a third system.
Okay, sir, thank you. Yes, sir.
Yes, sir.
তারপরে
তারপরে নিয়ে গেছে, নিয়ে যাওয়ার পরে তো বডি বলছে আমি প্রথম থেকে একটু সন্দেহ হয়েছে, এই জন্য আমি আমার গাড়ি নেই নাই। তো বলছি তোমার ইউনিভার্সিটি গাড়িতে তুমি আসো, বলছে তোমাকে উঠিয়ে নিয়ে যাবো, আমাকে উঠিয়ে নিতে লাগবে না, আমি যাবো। তারপর বডি ওদের সঙ্গে যায়নি আর কি, গেছে বলে আমি ওর সাথে যাইও নি, ওই ডাক্তারের চেম্বারেও একটু দেখা হয়েছে, পজিটিভ পেয়েছে। তারপরে মেধানিতে ভর্তি হয়েছে আর কি। ডাক্তার বর্মন বৌদিকে বলছে তুমি ঘরে যাও, তুমি ঘরে যাও, তোমার থাকতে হবে না, বলে ওরা আমাকে নিয়ে চিন্তায় করেছে। এরকম করে কি আমি ফেলে আসতে পারি, আমি জানিনি ঠিকই, তো দরকার হলে তো যেতেই লাগতো। পরে বলবো কি করতে।
See, there are different ways. The first law of thermodynamics can be stated. All right? So we write down the statements. I don't know how many statements are given in your textbook, but you should know. Okay, we'll write. The first law of thermodynamics is simply the law of conservation of energy. It can be stated in various ways. Okay. One. Energy can neither be created nor destroyed. Although it can be converted from one form to another. This is the most popular definition because it's very easy to remember. Second, the total energy of an isolated system remains constant. Why? Because it cannot escape. Although it can change. From one form to another form. Third, the total energy of the universe is constant. Fourth, whenever a certain quantity of some form of energy disappears, and exactly equivalent amount of some other form of energy must be produced. Right. It is impossible to construct a perpetual perpetual means continuous motion machine which would produce work without consuming energy. Okay. Enough for today. So